Welcome to AirHop rApp demonstration, AI ML-based dynamic energy management application for energy savings, powered by VMware Centralized RIC. As communication services providers, or CSPs, expand their RAN footprint to enhance connectivity and services, a major challenge to this journey is finding the right compromise between guaranteeing network accessibility and network performance versus the cost in energy consumption. Not enough resources, and users will fail to connect. Excess in resources, and the TCO will skyrocket. Ideally, CSPs would like the energy consumption to dynamically adapt to the mobile network service demand. But how? AirHop Energy Savings rApp, powered by VMware Centralized RIC, optimizes energy consumption in the RAN while ensuring users' quality of service. Leveraging AI-based learning and RAN programmability to predict traffic changes in the network, AirHop Energy Savings rApp automatically turns off or on RAN elements in the capacity carrier only when needed and without compromising users' experience. The business impact is immediate. Using AirHop's rApp, CSPs can reduce energy consumption for the delivery of its wireless services, all while ensuring user quality of service and customer SLAs. Moreover, CSPs will reduce their carbon footprint, resulting in operational sustainability and a greener network. So how does AirHop's unique technology work? First, the rApp trains the AI/ML energy savings model by ingesting historical RAN data composed of unique traffic demand profiles. These profiles characterize traffic demand by time windows, for instance, daily, weekdays, weekends, and by user types, such as business or consumer. Then, the application establishes a single trained model deployed as distributed inferences across the cells in the network. These deployed models are periodically updated based on two inputs. First, the new data about current network traffic demand, resource utilization, and configuration. And second, information on the trade-off between optimizing energy consumption and end-user quality of service. Finally, AirHop Energy Savings rApp makes an intelligent decision about the on or off state of the capacity carrier. As a result, the energy consumption of the RAN breathes with the traffic demand without impacting the user quality of service. In this demo, we are going to show 3 steps to highlight the capabilities of the rApp. Our testbed is composed of the VMware Centralized RIC, offering O1 and data management services to the application. Integrated through the VMware SDK, we have AirHop's Auptim rApp. Lastly, our testbed is completed using RAN emulation for O1 data, representing RAN configuration and performance. Let's activate this testbed. We first start with creating the energy savings model offline from the historical RAN data. The charts showcase the different episodes of the model creation. The AI/ML engine ingests accessibility data and proceeds to evaluate the trade-off between activating, deactivating power and achieving high levels of accessibility. After a small period of adjustment, accessibility and power curves stabilize. We have trained the energy savings model. Now we validate the performance of the trained energy savings model by applying a variety of traffic demand scenarios. In the top chart, the blue line represents the traffic demand, and the red line represents the decision made to activate or deactivate energy savings mode in the cell. As the traffic increases, the algorithm decides to disable energy savings. This explains the increase in power in the middle chart. And as soon as the traffic demand decreases, the decision made is to activate energy savings mode. We can see that at all times, accessibility is guaranteed. We now launch AirHop's rApp with the energy savings model on the VMware Centralized RIC. We can immediately see that rApp has successfully connected with the RIC, and it is starting to receive information about the topology of the network. For this demo, the rApp discovers a network composed of 150 cells. With a testbed up and running, let's see how AirHop's rApp automatically updates the capacity carrier from on to off state based on traffic conditions. As the RAN emulator proceeds to report QoS and traffic demand in the network, we verify that the rApp queries the RIC and obtains such data reports. As the data is collected for the registered cells, the rApp populates information about the current traffic demand, average throughput, and energy savings mode for each cell and its neighbors. In this case, the cell is currently in energy savings mode off. Now, after ingesting a few more rounds of network metrics, we can see how the rApp's algorithm starts to make decisions about the energy saving state of a particular cell. Looking at the rApp logs, we can see how cell number 51042 has been ordered to transition to energy savings mode. In the rApp GUI, we can confirm that the cell has transitioned to the energy saving state. Finally, let's see how the rApp updates the capacity carrier from off to on state based on traffic conditions. In this case, we can see that for certain cells, the algorithm decides to deactivate the energy savings mode given the traffic prediction made and the current cell's conditions. The rApp GUI confirms elevated traffic levels in those cells and the transition to the energy savings mode deactivated state. To summarize, in this demo, we have seen how AirHop's rApp trains and deploys an energy savings model based on historical data, and how it leverages this model with current traffic demand to make intelligent carrier activation-deactivation decisions based on the trade-off between energy savings versus end-user quality of service. The benefits are clear. Thanks to AirHop Communications Energy Savings rApp, powered by VMware Centralized RIC, CSPs can maximize customer experience and guarantee services SLA, while keeping energy costs under control and ensure a sustainable, greener network.